So we all know the answer to this, but what you've got to do in this particular case is you've got to make the algebra convincing enough to persuade the examiners to give you these 5 marks. So you can almost always write your answer dy by dx is equal to 4x minus 5, but you must make sure that the answer that you arrive, or the algebra you go through to arrive there, is convincing enough. You don't get any marks for writing that down. It all comes down to that fundamental idea that if you want to know the gradient of a curve at one particular point, then you have to choose 2 points on the curve and join them together with a straight line. And the gradient of that straight line is dependent on those positions. So we have, and we know that the gradient is, remember, M Monte, which is a climb, is the change in your y values of your change in the x values if you use the small change notation, or if you use xfx notation and you have a small change of h, this would be x plus h, f of x plus h, and that's if you're using function notation. So your gradient in that particular case is the difference between the y values, f of x plus h, minus the f of x, over the difference in your x values, which is x plus h minus x. And clearly that gives us that classic main. Now I'll go through it both ways. I personally prefer the first principles, the small change notation. So what I would say in this case is y is equal to 2x squared minus 5x, and a small change in y is caused by a small change in x. Working on the right hand side, if I expand that out, x plus delta x all squared is x squared plus 2x delta x, but I've got to multiply by 2, so it's 2x squared plus 4x delta x plus 2 delta x squared minus 5x minus 5 delta x. Just managed to squeeze it in. And of course that's y plus delta y. Now because y was equal to 2x squared minus 5x, that eliminates those things. I could take y off both sides, but because they're equal, I can just get rid of them. Now what that will leave me is delta y is equal to, now each of the terms that's left has got a delta x term in it, so I'm going to extract it as a common factor. 4x plus 2 delta x minus 5. So you can see that my answer is starting to come through. Dividing both sides by delta x, my small change vertically divided by my small change horizontally, 4x plus 2 delta x minus 5, and we have to allow delta x to tend to 0. My delta y over delta x tends to dy by dx, which is the gradient function, and any term that's got a delta x in becomes 0, hence dy by dx is equal to 4x minus 5. If I wanted to use the other version, which is the common one, f of x plus h minus f of x over, or all over h. Not sure why that line suddenly disappeared. I really should state first of all that f of x is equal to 2x squared minus 5x. So what I'm going to get here is 2x plus h all squared minus 5 bracket x plus h minus, I'm going to bracket this bit because there is a negative that will have to distribute, all divided by h. Alright, so again, expanding the top, x plus h all squared is x squared plus 2xh or hx, whichever you prefer, plus h squared. But I've got to multiply it by 2, so I'm going to get 2x squared plus 4xh plus 2h squared minus 5x minus 5h minus 2x squared plus 5x all divided by h. Okay, so I've got 2x squared minus 2x squared, I've got minus 5x plus 5x, and again I'm in the situation where I can draw h out as a common factor, h bracket 4x minus 5 plus 2h all divided by h, and as h tends to 0 I can get my required dy by dx equals 4x minus 5 because the 2h also tends to 0, and therefore I can get the answer I know. But you have to show all those points. Now be careful with the negative sign that distributes there, so the things to watch out for are that bit there and this bit here, depending on which technique you use. Doesn't make any difference. As I say, I personally prefer the x plus delta x version, but that is just a personal preference. Now this one's straightforward application of Wallis's rule, and Wallis's rule is you multiply by the power and you bring the power down by 1, but that is when you have them expressed in the index form. So y equals 16 over 5 x to the 1/4 plus 48 x to the minus 1. Now if I apply Wallis's rule, don't have to justify it, I can just stick it down. Okay, I'm going to get 16 over 5 multiplied by 1/4, bring the power down by 1, x to the minus 3/4 minus 48 x to the minus 2. Clear cancellation going on here. And then I've got to actually establish what numbers I'm going to use. Now, it's not a bad idea, so when x equals 16, dy by dx is going to be 4 over 5, 16 to the power minus 3/4, which your calculator will happily deal with, minus 48 over 16 squared, which is 4/5 times 1/8, minus 48 over 256. And that cancels down, so obviously you can, why have I written an 8 there? It's 4/5, silly person. I've got a cancellation going on here. This becomes 1/10 minus 3/16. And your calculator will do this, but 8 over 80 minus 15 over 80 equals minus 7 over 80. You need to show the steps. So for 3 marks, I'd expect to see at least 3 lines. I've got more lines in there. I could get away with, at a minimum, this line here, this line here. I really would like to see that line there, and then my final answer.
Good evening, or afternoon, or morning, depending on when you're watching this. You will have already done differentiation from first principles, and you will have probably looked at that up to powers of x cubed. That's on the specification for WJC, so you ought to have at least seen that or tried to do it. So very quick recap of that. So if we have f of x is x cubed, then f of x plus h is x plus h cubed, and that will be x cubed plus 3x squared h plus 3x h squared plus h cubed. And notice there that, and this will come back in a bit later on, we've got the, is that working? We have those coefficients which you may recognise. Okay, so dy by dx is the limit as h tends to 0 of f of x plus h, take away f of x divided by h. And we can see that if we subtract the x cubed, or the f of x, from the f of x plus h, the x cubed is going to disappear. So we have left over 3x squared h plus 3x h squared plus h cubed over h. And thanks to one of my esteemed colleagues, I'm now going to use my new way of showing this by taking the h and h out of that expression, which leaves us with h times 3x squared, which is what you can read anyway, so I'll move on. And then we're still divided by h, so at this point the h's cancel. Don't forget to put the limit in. It's very, very important. And then if we do let h tend to naught, this term will go to naught, this term will go to naught, and we're left with our 3x squared. Okay, so that's the recapy bit. Now, the other way that you might know that when you differentiate x cubed you get 3x squared is that you might have been told, you will have been told, or you'll have come across this rule, that if y is x to the n, then dy by dx is nx to the n minus 1. And you might be happy with that, because if we look at y and dy by dx, and if we look at, say, x and x squared, so x is of course x to the 1, and then we have x squared, and we have x cubed, and those are the ones that you've done. You've done these two from first principles. You've sort of done that from first principles, I guess, in examples. So if we do the rule, this becomes 1x to the 1 minus 1. That becomes 2x to the 2 minus 1, and that becomes 3x to the 3 minus 1. And so that's x to the 0, which is 1. So we just get 1 times 1 is 1. This becomes 2x. This becomes 3x squared. And so because you've done these by from first principles, then it's easy enough to accept that. But what about larger values of n? Are we happy to just say, oh, well, that pattern extends? And we might be happy if all we're interested in is doing questions from exams and that sort of thing. But if we're actually interested in the maths, then we need a bit more than just, oh, well, it looks like there's a good, decent pattern, so I'm going to accept this result here. And so I just briefly want to sort of extend from the idea of Pascal's triangle, which connects to, and I'm going to pause for you to think of the answer to this, what theorem or expression does it relate to? And you will probably now have remembered that it relates to the binomial. I may have said binomial a bit ago, I'm not sure. So the binomial theorem. The thing about Pascal's triangle is that if we started off we can see that down the side is always going to just keep going up like that. And so on the nth row, we are always going to get n there. Just clicking through. Yeah, so when we are looking at y equals x to the n, or f of x equals x to the n, then f of x plus h will be x plus h to the n, and this will start with x to the n, and then the coefficient, and you can see this in your formula sheet if you like. Hopefully you know the binomial theorem at least up to a point by now, but what you get is you get nx to the n minus 1 times h, and then every term after that, so if we just look at the next term, we have n minus 1 over 2 x to the n minus 2 h squared. I'm hoping that's still on the screen. If it isn't, you'll have to work it out for yourself, because you can look at your formula book if required. But the point is that every term after that will have at least an h squared in it. So we can now write f of x plus h as x to the n plus n x to the n minus 1 h plus h squared times something. And so when we are working out what f dashed of x is, or dy by dx, in this case, we're going to be subtracting the f of x from the f of x plus h. So that means that this term and this term will cancel out, and we'll be left with n x to the n minus 1 h plus h squared times something, all over h. And now we can cancel the h. Oh, limit. Now, you may be wondering why somebody who's trying to teach you maths keeps sort of forgetting to put the limit as h tends to 0 in, but of course I'm not forgetting. I'm deliberately not putting it in to mimic a student who keeps forgetting to put it in, so that they remember to put it in the future. Anyway, if we cancel the h, we can cancel that h with that h. The h squared divided by h becomes just an h. And when we let the limit tend to naught, all that disappears, which leaves us with nx to the n minus 1. So, linking that back to the binomial again, the reason why this rule that we're using here works for whole numbers of n at least is because all those other terms for the binomial will have powers of h of 2 or more, and because the coefficients start with a 1 at the beginning and then this n here. And so you've now seen the a sort of proof, let's call it a proof for now, of the general form of dy by dx from first principles for positive integer n. So you've got to be very precise in mathematics if you're going to study it further.